This is a video on the matrix topic that we've been working on, and we're going to have a look at, very briefly, an introduction to the unit matrix, and then we're going to look at a problem where that's involved. The unit matrix is effectively, in matrix terms, the equivalent of the number 1. When we talk about the unit value in number, we're talking about 1. The unit matrix, which you usually use capital I, is a matrix such that, as it says here, if you multiply matrix A by I, you end up with matrix A. And it doesn't matter which order. Hopefully you know already that the order of multiplication is important, but it doesn't matter if we multiply the unit matrix before or after a given matrix. You multiply that out and it will actually give you the same value, which is the same effect as multiplying by a number by 1. Now, what does it look like? Well, you can see here that a unit matrix is a square matrix, and the properties of it are that the principal diagonal, which is the one that goes from top left to bottom right, all contain 1, and all other elements are 0. So a 2 by 2 unit matrix has 2 1s and 2 0s, and a 3 by 3 matrix has 3 1s and 6 0s. Just to kind of show the idea here, if we defined A as a matrix 3, 2, negative 1, 5, then if we were to say AI 3, 2, negative 1, 5 multiplied by 1, 0, 0, 1, if we think about the elements, it's a 2 by 2 matrix and a 2 by 2, so therefore that's going to give us a resultant 2 by 2 matrix. Just very quickly then, the answer would be multiplying those two there. 3 times 1, which is 3, plus 2 times 0, which is 0, so I would get 3. Multiplying the row 1 by column 2, 3 zeros are 0, and 2 times 1 is 2. And then multiplying through second row, first column, negative 1 plus 0 is negative 1. And then the last pair is 0 plus 5 is 5. And if you look, we've got the same matrix as we started with. So multiplying by the unit matrix doesn't change a value. What's its use in a way? Well, there are certainly uses where we're looking at the differences in multiplying the unit matrix by some kind of constant term, which then creates effectively a kind of constant multiplier that we can use. So here's an example. We have a matrix, and we're asked to show that in this identity A squared is equal to some multiple of the original matrix A plus some multiple of the unit matrix I. So we need to kind of think what would the values of P and Q be in this problem here. So the first thing would be to have a look at what A squared actually gives us. So A squared would be matrix A multiplied by matrix A. 2 by 2 multiplied by 2 by 2 is going to give me a 2 by 2 matrix as well. And going through the motions here, first row, first column, 1 times 1 plus 2 times 3 is 7. First row, second column, 1 times 2 is 2, plus 2 times 1 is 2. That gives us 4. So I'm going to have 4 in my next element. Down on the second row, 3 times 1 is 3, plus 3 times 1 is 3, which is 6. And the last element is going to be 3 times 2 is 6, plus 1, which is 7. If you're not sure about the multiplication aspect, go back and look at the previous examples. So A squared is the matrix 7, 4, 6, 7, and we want to represent it by a certain number of P times A plus Q times I. we'll take that separately and think, well, P times 1, 2, 3, 1 plus Q times our unit matrix. And if we multiply them in, we would actually get P, 2P, 3P, and P plus Q, 0, 0, Q. And if I add those two matrices together on the right, I would actually get one single 2 by 2 matrix whose elements are P plus Q. That's me got the first element here. P plus Q is just P plus Q. 2P is going to be on its own there because we're adding 2P and 0. In the second row, we've got 3P plus 0, and we've got P plus Q. So we've got those things here. So we're saying that those two matrices effectively are equal. So we're saying that this matrix here is equal to this matrix here, which means that we can actually directly equate each of the elements from one to the other. We can map the first element of this matrix here, P plus Q, I need a different color. P plus Q must equal 7, and 2P must equal 4. And there's sometimes in these kind of situations an easier way to get into this situation. So if we're saying that if a squared, well, we should use as because we're told it does, I'll say 4 is probably the best. For a squared equals P a plus Qi, then what we can say here is a couple of things. We can say that P plus Q, let's get them there, P plus Q equals 7, and if we look at the second one that I've highlighted, 2P equals 4. Now we've got two unknowns. Two different equations would be sufficient in order to solve it. You might have to do it simultaneously if you've got P and Q in both of them, but in the second one here, it's quite clear that 2P is equal to 4P is the value of 2, and in that case there, we can say that 2 plus Q equals 7, so Q equals 5. In other words, we can say that a squared is equal to 2a plus 5i. And that is us finding the values of P and Q. And we can check that if we wanted. 2a would be 2462. 2462, that's 2a. And 5i would be 5 times the unit matrix. And if we put them together, we get 7467, which is the same as a squared. Okay, so that's a nice wee algebraic process using a bit of matrix arithmetic in order to solve that particular problem.